This lesson is on triangles and quadrilaterals. We're going to start with something called the triangle angle theorem. First, we're going to talk about how to deduce it yourself. Then we'll talk what is the definition of it. We're going to formally prove it. And finally, talk about how we can use it. Next, we're going to talk about how to classify triangles by angle or by side. And finally, classifying quadrilaterals. So let's start with deducing the triangle angle theorem. To do that, get a piece of paper and cut it into a triangle. It doesn't matter what kind of triangle. It doesn't have to look anything special. Just any old triangle will do. And then number the angles and tear them off so that it looks like this. So we're going to number those different corners, the angles, and then we're going to tear this triangle into 3 different pieces. Now place the 3 angles adjacent to each other to form one angle like this. Now, what kind of angle is formed by these 3 smaller angles? What is that angle's measure? And then you need to make a conjecture about the sum of the measures of the angles of a triangle. And what you can tell is that the sum of the measures of the angles of any triangle is 180 degrees. And that is called the triangle angle sum theorem. So if we have a triangle, the measure of angle A plus the measure of angle B plus the measure of angle C, all that together equals 180 degrees. And like I said, it's for all different kind of triangles. You can try it with many different kinds of triangles on our first thing of cutting out a triangle, and it will always work. The proof of a triangle angle theorem is if I take a triangle, ABC, and it has 3 angles, angle 1, angle 2, angle 3. I'm going to draw a line L through C so that it is parallel to line AB, so it looks like that. Now, note that angle 1 is congruent to angle 1 prime. Why is that? Because they're alternate interior angles, and alternate interior angles are congruent. Also note that angle 2 is congruent to angle 2 prime. Again, why is that? Because of the alternate interior angle theorem. Alternate interior angles are equal, or their measures are equal. Now note that angle 1 prime plus angle 3 and angle 2 prime together, they form a straight line. And straight lines have 180 degrees. So if angle 1 prime and angle 3 and angle 2 prime together add up to 180 degrees, then the same thing must be true for angle 1, angle 3, and angle 2. Now let's do a 2-column proof. This is a kind of formal proof that we'll do later in the year in a different unit. 2-column proofs have statements, and they have reason for those statements. So the first statement is going to be about drawing a line through C that is parallel to line AB. So I say create a line L that is parallel, such that it is parallel to line AB. And the reason for that is that through a given point, there exists only one line that is parallel to another line. So it's not like there can be two different line L's. There's only one. Next, I'm going to say that angle 1 is congruent to angle 1 prime. Why is that? Because they're alternate interior angles. I'm going to do the same thing with angle 2 and angle 2 prime. They're congruent. Why? Because they're alternate interior angles. Next, I'm going to note that the measure of angle 1 prime plus the measure of angle 3 plus the measure of angle 2 equals 180 degrees. And that's because of the angle addition postulate. An angle equals the sum of its parts. Finally, I know that angle 1 plus angle 3 plus the measure of angle 2 equals 180 degrees. And I know that through substitution, because earlier I talked about that angle 1 is congruent to angle 1 prime, and angle 2 is congruent to angle 2 prime. So this is a formal 2-column proof, and again, we'll do these later in the year. Now, how would you use the triangle angle theorem? Let's say I have a triangle there, and I know two of its angles, 70 degrees and 45 degrees, and I'm trying to figure out the third angle. Well, I know that the sum of all three angles is 180 degrees. So 70 plus 45 plus x, I'll call the question mark x, equals 180. Do a little addition, combining like terms, so I know it's 115 plus x equals 180. Subtract 115 from both sides, and I end up with x equals 65. So that missing angle is a 65-degree angle. Here's another problem. Once again, I know that all three angles sum to 180, so 45 degrees plus x plus 52 degrees plus 90 degrees equals 180. I know it's 90 because of the right angle sign in the bottom right-hand corner. Again, I need to combine like terms. 45 plus 52 plus 90 is 187, and my x is the only x there, so it's just plus x equals 180. Subtract 187 from both sides, and I'm left with x equals -7. Now let's talk about triangles. And triangles are put into different groups or categorized by either their angle, and so if all three angles are congruent, it's called an equiangular triangle. If all the angles are acute, it's called an acute triangle. If one of the angles is a right angle, it's called a right triangle. And if one of the angles is obtuse, it's called an obtuse triangle. And since earlier we learned that a triangle can't have more than 180 degrees, then it can't have two right angles, or two obtuse angles, or a right and obtuse angle, because that would be not enough. Or if it was two right angles, that would already be 180 degrees, and there'd be nothing left for the third angle. And if it's two obtuse or a right and obtuse, then that's more than 180 degrees already. So it can only have one obtuse or one right angle in it. We can also categorize not only by angle, but by its sides. If it is all the sides are congruent, it's called an equilateral triangle. If two sides are congruent, it's called an isosceles triangle. And if no sides are congruent, it's called a scalene triangle. Notice that an equiangular and equilateral triangle are actually the same thing. And so we don't actually use the name equiangular. Instead, we call both equilateral. So an equilateral triangle just means it has all the angles are congruent and all the sides are congruent, but by convention we just call it an equilateral triangle. And finally, we can name things by both angle or side. So for example, there's an acute scalene, there's an acute isosceles, there's a right scalene, a right isosceles, an obtuse scalene, an obtuse isosceles, and finally the equilateral triangle. Just as I categorize triangles, I can also categorize quadrilaterals, and there are several special types of quadrilaterals that we need to talk about. The first is called a parallelogram. It's a quadrilateral with both of its pairs of opposite sides are parallel. So you can see that the side on the top and the bottom and the side on the left and the right are parallel with each other. The next type of quadrilateral is called a rhombus. A rhombus is a parallelogram, but it's got four congruent sides. I was always taught to think of a rhombus as a square that an elephant sat on, so it sort of crushed it over to the side a little bit. So all of its sides stay the same, and it's a parallelogram. A rectangle is a parallelogram with four right angles. So its opposite sides are parallel, and each of its angles is a right angle. A square is a parallelogram with four congruent sides and four right angles. So it's both a rhombus and a rectangle and a parallelogram all together. That's a square. A kite is a quadrilateral with two pairs of adjacent sides congruent and no opposite sides congruent. So those two sides on the left are congruent with each other, and those two sides on the right are congruent with each other, but the side on the left and the side on the right are not congruent. Also, notice that this is not a parallelogram. It's the first kind of special triangle, special quadrilateral we have that is not a parallelogram. Finally, we have a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. So the example over to the right there, the top and the bottom sides are parallel, but notice that the left and the right ones are not. And just as we had an isosceles triangle with two sides that are congruent, an isosceles trapezoid, which is an example of the one at the right, is a trapezoid whose non-parallel opposite sides are congruent. One way to think about these quadrilaterals is a diagram that will show you the relationships between them. So we start with just a regular old quadrilateral that has no parallel sides, the sides aren't equal, nothing special about the angles, just a four-sided shape. Off one branch of that, we have a kite, which has no pairs of parallel sides, but it's a special parallelogram because it has, in this case, the two top sides are congruent and the two bottom sides are congruent. Next, it could have one pair of parallel sides. So there's a trapezoid there, and then a special kind of trapezoid branching down from that is an isosceles trapezoid. So it's got the side on the left and the side on the right are congruent. So on the far left, we have no pairs of parallel sides. In the middle, we have one pair of parallel sides. And now the branch to the right, we have two pairs of parallel sides, and that gives us a parallelogram. A rectangle is a special kind of parallelogram that has the four right angles. A rhombus is a different kind of parallelogram. We don't know anything about the angles, but we know that its four sides are the same. The four sides are congruent. Then a square is both a rectangle and a rhombus. It's got four right angles and four sides that are equal.